So this is the highlight of the entire semester, I like to say. In the last video, what we have learned is that change in magnetic field actually induces electric current, therefore electric voltage, right? So you don't need to have a voltage source. All you need is the closed loop, and then inside the loop, if you have a change in magnetic field, then the current will be induced. You have a voltage that's induced, and you have a change, but you have to have a change in magnetic field. If the magnetic field is, no matter how strong it is, if it's just stationary, you don't have anything that's induced. But anyhow, the change in magnetic field, you know that it's going to be having a voltage induced. But think about it. If the voltage is induced and you have an electric current that's running, let's say on the top of the loop here, let's say the induced electric current is running this direction. Don't we need to have an electric field? There is an electric field. That's why there's going to be current, right? The electric charges feel the electric field. That's why they have a force, and that's why they move. So if you have on top of the loop here, if there is an electric current that's running in this direction at that moment, that means that you have an electric field that's induced at that time. So change in magnetic field induces electric field. Change, but remember that though, when you had a change in electric field, what happens? You also have magnetic field induced, remember? So they mutually induce each other. Change in magnetic field induces electric field. Change in electric field induces magnetic field. All right, let's go into the board and organize our thinking. And so it was done by the Faradays that put an idea of electric field in electric current induction, but it is Maxwell that put everything all together into one thing that says that when you have an electric field, changing electric field, you're going to have a changing magnetic field. Two together, and let's imagine when you have a charge that's moving up and down, constantly moving, right? Which is called oscillation. Then the motion of electric charge induces magnetic field. But you have electric charge that's moving, so you're going to have electric charge. You're going to have electric charge, so you're going to have electric field. So all these things I'm going to write on a whiteboard, so stay with me, and I'll see you in the whiteboard, okay? Wait, sorry. Okay, I'm going to share the whiteboard. Yeah, so remember I talked about this thing, the coil, and then there's a magnet. I don't want to lose that magnet. But let's say the magnet is coming towards you, right? So that means that there's going to be an increase in magnetic field that's coming towards you, coming out from the screen. Then which direction is the induced current will flow? Okay, so I'm going to write it in here. We have a coil here. I'm going to use the purple. This is the closed coil. We have a light bulb connected. And then when we put the magnet in it, so this is the notation. Oops, I'm going to make it larger. this is the notation into the board. So it's coming perpendicularly into the board, into the page. By the way, this is out of the page. So magnetic field is coming in this direction inside the loop by putting magnets in it, right? So that's increasing. Which direction will the induced current flow? All right. It doesn't like, the coil doesn't like the change. So therefore, if it's coming out this way, then it wants to create, to prevent it. So it wants to do this way, right? Then that means use your right hand rule. The current will flow. Different color would be good. Green I've used. Let's see. Blue. Make it thicker. So then the current will flow in this direction. Induced. Does this make sense? So current will flow in that direction using the right hand rule. So at that moment, when you have a current flowing, then let's look at this point. You're gonna have electric field that's pointing in that way so that the current can flow in that direction. At this location, you're gonna have electric field producing that way. So you do see that there is an induced electric field. But you also know when you have a change in electric field, whenever you have a charge in motion, you also produce magnetic field. So let's think about this case now. I'm going to have, let me not share. Let's look at this pen. What's this pen tip made of? Metal. What does metal have? Free electrons. Free electrons are electric charge. What will happen if I move this pen up and down, up and down, up and down, up and down? What am I doing? If I'm just staying here, well, it's just the charge plus and minus is the same, so it doesn't do much. But if I'm moving this electrons moving up and down, up and down, up and down, up and down, there is going to be change in electric field. There's going to be a change in electric field. So if I move it up, electric field up. If I move it down, electric field down. Electric field up and down, up and down, up and down, up and down. Each time I'm moving, I'm creating, generating, oscillating electric field, right? Then what happens when I have a change in electric field? Electric field is constantly changing up and down as I'm moving the pen up and down. And the direction is this way, up or down. But if I have a change in electric field, that also generates magnetic field. And remember the relationship. The magnetic field would be either coming out or in as I move up and down. And this electric field that initially it's generated in this way, later time will be, you see the electric field line, electric field, it's almost instant. We always think that it's almost instant. I said the electric field travels though. It travels. So it's not infinite. You can send out the information about electric field. It still has a limit, and that's 3 times 10 to the 8 meter per second, 2.99. But it still goes, you have a limit. That's the speed of light. Anyway, the electric field has a limit, and then when it's just generated in this direction, as I move it up. And then later on, I'm moving down. But this initially, when it's just generated here, it's traveling in this direction. And then when I'm moving down, the next one is coming in this direction. And the next one is coming up and down, up and down, up and down. At the same time, magnetic field is generating this direction. That's also move along with the electric field. And then when it's moving down, it's going to be into this way. And then it moves, 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 moves. And this is called electromagnetic wave. I said it, it's electromagnetic wave. And that is light. The light is electromagnetic wave. And it's everything put together by Maxwell. So I'm going to show you let me see. I'll show you in a whiteboard first. So imagine we have a charge, electric charge here. And that's moving up and down and up and down and up and down and up and down. As the electric charge moves up and down, at that moment when it's just starting to move, the electric field line is going to be pointing in that direction. Right? The electric field line is going to be pointing in that direction. And then it's going to be, this one is going to move to the right or to the left in both directions. But it's going to be propagated 3D. But anyhow, tell you how they move. But so it's going to be moved. It's going to be moved. The signal will be traveling throughout the space, right? So then later on, this is going to be at here. But at the same time, this electric field now is going to be bigger. Because it's going to move even higher. So you're going to see the electric field is built up something like this. And then it's also going to move downward. And come back up. Because you go move it up and down, up and down, and up and down, up and down. Right? So this is at a certain time in a space that this charge is going up and down, up and down, up and down. At the same time, perpendicular to the electric field, magnetic field is produced. Something like this. And this is called, let's use red, electromagnetic wave. Field, changing electric field, change in electric field. Induces change in magnetic field. They oscillate together and propagate together. They oscillate together, and propagate together. And it is Maxwell that put this Faraday's law and all that stuff together mathematically. But it's been proven experimentally too. And you see, we use this everywhere. But this is the light. There. So all this light is made of electromagnetic wave, and its source of electromagnetic wave, you see the source of electromagnetic wave is the oscillating, I guess it doesn't have to oscillate, but oscillating electric charge. So simply, I could just have a pen like this that has the metal, and the metal has free electrons. So I just move this free electrons, electric charge, fast. I am generating electromagnetic wave. So that's the highlight of this semester, that I put all the ideas together and you see what light is made of. I'm going to stop sharing. I plan to do further talking about light and all that, but for now, for this video, this is the highlight, and then I'll end it here. Before that, maybe let me share this picture of a better look of electromagnetic wave. Ooh, that just doesn't sound so good, huh? Sorry about that. Okay, so this is electromagnetic wave. You have an electric field that's drawn in pink color, that's oscillating with time, and the blue is that's oscillating magnetic field together with the oscillating electric field. And you see that these information of a changing signal is going to be propagating. It's going to propagate. And I told you that the speed of the propagation is 3 times 10 to the 8 meter per second. All right. So thank you for sticking with me, and this is going to be the end of chapter 25 video. See ya. Let me see.